Hello everybody. Now we shall discuss about measurement of self-inductance. Measurement of self-inductance. The following bridges can be used for the measurement of self-inductance. Maxwell's inductance bridge, Maxwell's inductance capacitance bridge, Maxwell's inductance capacitance bridge, Hayes bridge, Owen's bridge, Anderson's bridge. These bridges can be used for the measurement of self-inductance. Before going to discuss about this Maxwell's inductance bridge, let us discuss about the representation of practical inductor and ideal inductor. Okay. Coming to the representation of ideal inductor. Ideal inductor. This is the representation of ideal inductor. Ideal inductor can be modeled like this. It can be modeled like this. It is pure inductor, ideal or pure inductor, representation of pure inductor or ideal inductor. Coming to the representation of practical inductor, representation of practical inductor. This is the representation of practical inductor. There is no ideal inductor in reality. In practical, there is no ideal inductor, because any inductor is after all a coil. It's just a coil. It's just a coil and is made up of some conducting material. It is made up of conductor. As this inductor is made up of some conductor, that conductor must have some resistance. Okay, that's why practical inductor can be represented like this: R L. This practical inductor has some resistance and it is exactly equal to the resistance of the wire used to wind the coil. How can we construct a physical inductor? Okay, you take length of wire. If you take length of wire, if you wind into a coil, if this you take a length of wire and wind into a coil like this, okay, nothing but inductor. Okay, so physical inductor can be constructed like this. Okay, you take length of wire, this is length of wire, you take length of wire and if you wind this length of wire into a coil like this, nothing but physical inductor. Okay. So, as this inductor is made up of conductor, any inductor is made up of conductor, and any conductor must have some resistance. That's why resistance is connected in series with this inductor. Okay, this will be the representation of practical inductor. Okay, this is practical inductor has some resistance and it is equal to the resistance of the wire used to wind the coil. Okay, resistance of this wire. Okay, and then you can represent inductor like this, including the resistance of this inductance and resistance of this coil. This resistance represents the resistance of this coil. Okay, so this is the representation of practical inductor. Okay, now let me discuss about Q factor, quality factor. Q factor. Q factor or quality factor. Q stands for quality. Q factor or goodness factor. Goodness factor. Okay. Q factor or goodness factor. Q factor is a measure of goodness. Okay, it is a measure of goodness. Normally, this Q factor is used for practical inductor. Normally, this can be Q factor can be used for practical inductor to check the quality of that practical inductor. Okay. So, normally used for practical inductor. Okay, Q factor is a measure of goodness. That is how good something is. This something is nothing but inductance. Okay. Here Q factor gives how close this practical inductor to ideal inductor. Okay, that is given as Q is equal to omega L by R. If this is R, if this is L, R is the resistance of this coil, L is the inductance of this coil, then Q factor is given as omega L by R. If R is small, Q will be more, or if L is more or L is large, Q will be more. Okay, in ideal conditions, to get high quality factor, R is 0. In this case R is 0. In case of ideal inductor R is 0. Okay, Q will be infinity. Okay, whereas in case of practical inductor, to make Q high, R should be small. R should be small. This should be small when compared to L. Okay, this should be small. R should be small when compared to L. L should be large. Okay, R should be small, L should be large. Then quality factor will be high. Okay, it measures the quality of the inductor. Okay, Q is given as omega L by R. In order to get high quality factor, resistance should be small. Now let us discuss about Maxwell's inductance bridge. Let me draw the Maxwell's inductance bridge. AC voltage given to this bridge. E is the voltage given to this bridge, AC voltage, AC supply. Let this is R1. You are going to have 4 arms, R1, L1, R2, L2, R3, R4. Let I1 is the current flowing to this, I3 is the current flowing to this branch, I2 is the current flowing to this branch, I4 is the current flowing to this branch. Voltage across this branch, let E2 is the voltage across this branch, let E1 is the voltage across this branch, let E3 is the voltage across this branch. Let E4 is the voltage across this branch. Okay. Now under balanced conditions, under balanced conditions Z1 Z4 is equal to Z2 Z3. When no current is flowing to this detector, the bridge is said to be balanced. The bridge is said to be balanced when no current is flowing to this detector. Okay, let the current which is flowing to this ID is 0. No current is flowing to this detector now. That is, the bridge is said to be balanced. Okay, Z1 Z4 is equal to Z2 Z3 under balance conditions. Okay, then what will be Z1? Z1 is R1 plus J XL1. What is Z4? R4. What is Z2? R2 plus J XL2. What is Z3? R3. This is nothing but R1 plus J omega L1 into R4, which is equal to R2 plus J omega L2 into R3. R1 R4 plus J omega L1 R4, which is equal to R2 R3 plus J omega L2 R3. Equate both real and imaginary parts separately. Imaginary parts separately, then R1 R4 is equal to R2 R3 and L1 R4 is equal to L2 R3. From this, what will be R1? Here R1 is unknown resistance, L1 is unknown inductance. Okay, so R1 will be equal to R2 R3 by R4. What is L1? L1 is equal to L2 R3 by R4. Okay, what is R1? R1 is equal to R2 R3 by 4. R2 R3 by R4. This is R1. Coming to L1, L1 is equal to L2 R3 by R4. Okay, L2 R3 by R4. Okay, here R1 is unknown resistance, whereas L1 is unknown inductance. Now here see, R1 is equal to R2 R3 by R4, L1 is equal to L2 R3 by R4. Okay, R3 R4, R3 R4, these two are common in both equations. Okay, these two terms are common in both equations. Okay, so if you vary R3, this shows variation of R3 shows effect on L1. If you vary R4, this shows effect on R1. Okay, so don't vary R3 and R4 because these two terms are common in both balance equations. Okay, so you vary R2 L2. So if we choose R2 L2 as variables, the two balance equations are independent of each other. To make two balance equations independent of each other, you choose R2 L2 as variables. Okay, then now R2 L2 are variables. Okay, so R2 is variable resistance, L2 is variable inductance. R3, R4 both are known non-inductive resistances, non-inductive resistances. Okay, now coming to the advantages. By using this bridge, you can find unknown resistance and unknown inductance. Okay, coming to the advantage, balanced equations are balanced equations are simple. Here balance equations, here see, no frequency term is present here. This is also independent of frequency, this is also independent of frequency. So balance equations are independent of frequency, independent of frequency. No variable capacitor is present in this bridge. No variable capacitor is present, so that the cost of bridge is lesser. Cost of bridge is less. Coming to disadvantage, this bridge is not suitable for the measurement of Q factor. Quality factor cannot be measured, as variable capacitor is not present in this bridge. There is no variable capacitor in this bridge. That's why Q factor cannot be measured, cannot be determined. Okay, this bridge is not suitable for the measurement of Q factor, as variable capacitor is not present in this bridge. Thank you.